Welcome back, everyone, for High Performance Computing, Advanced Scientific Computing. Today we have our practical lecture 01, which is basically covering a little bit an introduction on UNIX, on SSH, just because we're using these sort of, let's say, ways how to use a computer very much in the course, and it's a kind of pre-lecture really to our real course material. So of course, the dependency with HPC is strong, but of course you can use UNIX and SSH, of course, without any HPC system. Still, it's important to think about these and know a little bit the way around with these. And my hope is also during the lectures, you will also learn to operate in UNIX and learn basically the SSH much more than you perhaps previously have. So I think people that are already, let's say, in having some Linux derivative, they are very fine in this. They probably understand UNIX, but many people in the course usually also operate only in the Windows environment. And that is not how usually a HPC system works. That's why we will talk today a little bit about UNIX and the SSH, just to understand how to access HPC systems which are remote and basically understand the basic tool set of a UNIX environment. But before we enter the material of this lecture, let us just review a little bit what we had in the prologue, where we basically covered the whole course motivation and give you lots of information what the course is all about. And if you remember, we talked about high performance computing as a field of constant changes. So basically always at the forefront of computing, new technologies from multi-core CPUs now to many core GPUs to storage hierarchies, lots of interesting new technologies. And the course will really looking into these technologies, of course, but also there will be a second part, which you see here a little bit explained in all this different application area, where you basically see climate and weather prediction. You see computational fluid dynamics here on an aircraft, but also on crash tests, for instance, or the evolution of smoke that we had the last time. So basically this represents these domain-specific science and engineering problems or domains, if you want, that really use HPC in practice daily and required really in order to solve a computational problem like we have seen, for instance, here, the evolution of smoke in a tube or so. A very specific field also in light of accelerators, which really driving a lot of these activities will be deep learning. We will look a little bit into this AI technology, not as a really deep course on deep learning. Obviously, you still have to do a proper course on deep learning or on machine learning in general. But here we will basically emphasize on the fact of how to use accelerators and many of those in order to tackle a problem. Throughout the course, you will also distinguish then HPC more and more, I guess, from clouds. Some of you have taken my course, Cloud Computing and Big Data, here at the university. So there we did much more HTC, high throughput computing. HPC is often recognized really by the fact that you see this black interconnections here. No matter which HPC system you look at, usually chances are that the interconnection between the different cores, between the different racks is really extraordinary. We're talking there about specific interconnects like InfiniBand. I will talk about it, of course, in one of the next lectures. But then this is really an important factor. And once you have these connections, you can also do certain ways of parallel programming in these different scientific domains, which is a little bit explained here in this interesting graphic, where you have all the different domains more or less sitting here on these different systems. And of course, there's a specific way how you use these systems in parallel with each other so that you don't run only on a couple of cores, but maybe on thousands of them. And we discussed very briefly that this is something called the message passing interface that we will also have as one of the mainstream first assignment basically for you in the course. In generally very important in the parallel computing, scientific computing domain. So message passing, as the name suggests, sends a lot of messages. You see here basically the source and the sink, but also we learned the last time briefly that there's actually also collectives to consider. But then another way of programming it is shared memory. So you would have shared memory systems where you basically have different threads that then can access the shared memory space. But obviously, this is limited to basically having access to shared memory. If you have another core somewhere else in another rack, it obviously cannot access the other shared memory part. So what happens is that people combine these techniques called hybrid programming, so that you have shared memory programming where it is possible, and then combined with distributed memory programming where you then send messages on these different clusters. And how this all fits together. And there's a new way of programming it now with the so-called accelerators, GPUs, that is a little bit suggested here, where you first upload, let's say, a problem or a so-called kernel via the main memory from the CPU to the device memory, and then to be basically executed on this GPUs, which is a many core systems, often with, let's say, moderate performance, but really in the thousands. And that makes it really, let's say, very much optimized for certain problems, like we have talked about matrix multiplication in deep learning, and we will have a lecture on this. But let's come back a little bit before we go into these materials of all these different lectures and have one of the first practical lectures where I demonstrate a little bit how you basically operate a little bit in the UNIX environment, how you access a remote HPC system. So obviously, UNIX is a very large subject. So if you basically want to have a whole course on it, you will see that we can easily fill this with files with, the inode system, up to other UNIX elements, commands, and so forth. So here the goal is really what is essential, let's say, for the HPC course here, in order so that you can make your baby steps. So we will do things like host names. We will do things like how I can list files, how I can create directories, and move along the space in so-called file systems. Also, this is these days not so obvious, as I learned throughout my last years of teaching, because many people here and there don't have anymore even a laptop anymore, but just smartphones. And in smartphones, the world of files is in a way not anymore existing. So you just trust everything with these apps, and you don't have access to files. You don't know how to deal with files, how to do directories. So that's something really for those people also that don't really previously have been accessing so many of these interesting areas in file system handling, will be an interesting part of the course. And of course, I encourage you to look more into UNIX if you want to work in the field of HPC. I mean, basically, UNIX is something what you really have to do. And basically, the SSH goes the same way, although there are very new, fancy ways with federated identity, how you log into different systems, how you avoid to have maybe SSH keys and so on. Still, chances are that in one way or another, you have to use SSH in some form at some system sometime. So with this, we look also into this secure shell. We will understand the private public key pairs, which give rise basically to this usage of SSH keys. And then I will show you how we access the system courses, HPC machines, which is Deep and Jötunn. And of course, there are different ways how you access these systems as username password in Jötunn, but also I will show you the handling with an SSH key and also system for it called an SSH client that is mobile extern. So a very practical lecture. Again, it's more or less a basic lecture. You can reuse this UNIX skills and this SSH skills, of course, for many different aspects as well. It don't need to be HPC, but for us, it's very relevant. So what about UNIX and HPC systems? When we think about this, this is really a core ingredient in the environmental tools. So basically, Windows had some HPC servers, and they're still here and they're existing, but let's say this is really rare, right? So here is really learning, perhaps the most important HPC environment tool in a sense, because the majority of systems, when you access them, are basically UNIX. Now, with Jupyter notebooks in AI, some people have found a way around that. So basically, you can use Jupyter notebooks and maybe don't use UNIX if it's all proper installed. But then you want to go into scaling, maybe to different GPUs usage from 128 GPUs suddenly, and then you're back on the UNIX environment, maybe have to edit job scripts. And this will be, of course, another part where UNIX fits in when we have this job scripts for batch job scripts really edited. Of course, this is not obvious to you. We'll see how that materializes in the next practical lecture 1.1, which will be following after the introductory lecture. There we will go much into scheduling, into batch submission. What does it mean to have batch, and so on. But before we do this, it's really important to think a little bit about Unix to just get a way of using this. And by this, we really understand how high performance clusters really work. So also thinking about that, here's a small interesting video that gives you perhaps also a good overview about this. So let's look at this a little bit about the deep, because the deep systems is also one of the systems that we were going to use in the course for your assignments. So listen carefully.
The questions we are trying to answer and the challenges we are facing to solve are more complex than ever. In today's world, we constantly generate large amounts of data in order to understand the world around us, and we need computing to read and store this data. But the nature of computing is changing, with an increasing number of data-intensive critical applications. By 2020, 25 billion devices will be connected and will generate over 2 zettabytes, 10 to the power of 21 bytes of traffic every year. High-performance computing, called HPC, is also known as supercomputing and involves thousands of processors working in parallel and orchestrated to analyze billions of pieces of data in real time. This means those supercomputers are performing calculations millions of times faster than a normal computer. The next generation of supercomputers, exascale supercomputers, will be performing 1 millions operations per second and are expected to be available around 2022-2023. Areas of application that require such complex and powerful operations are, for example, earth sciences, health sciences, climate and environmental research. In those cases, it is being used to make much more accurate forecasts than available today through simulations and visualization of data. This allows us, for example, to have a better understanding of the processes involved in climate change and to predict the change in our climate more accurately. Who is developing now the concepts and technologies needed to build exascale computers? Among others, a consortium of research centres, universities and industrial partners from 8 European countries, called DEEP projects. The Jülich Supercomputing Centre is responsible for the coordination of these projects. The EU is supporting the development of supercomputers in order to stay ahead of the global competition. The main 3 pillars of supercomputing are the exascale technology, easier access to HPC for all qualified users, further development and knowledge transfer from and to HPC applications. A future with supercomputers is essential to better understand our environment, safeguard our health, maintain our mobility, and help industry develop sustainable products in less time. In the digital era, supercomputers are the core of major advances, innovations, and a strategic resource for Europe's economic and technology future. The DEEP projects are contributing to make it happen.
All right, I think we heard enough. So this was a specific example from a specific HPC system from a consortium, as you heard, that is developing this DEEP system. And of course, this is something we're going to use in the course, and that's why I put an emphasis on it. But of course, many of the things we will learn here, including this network interconnection that you see in the HPC systems, is of course relevant for many other HPC systems worldwide. You will see in one of the introductory lectures that we basically have infrastructures like PRAISE, where people in HPC in Europe really stand together, but also, having then centers in Sweden, having centers in Germany, France, Italy, basically for HPC, particularly with really large systems. And in this, we basically join forces also with skill sets, as you heard, and then also applications. But once, one step after another. So we basically now want to get the baby steps right for Unix. And just to give you a little bit, of course, then an understanding what a HPC system is. is also a bit important here. So you can imagine a HPC system is not like a laptop. It's not standing under your desk. And with this, it's a resource which is usually remotely. So we have to find ways of accessing this system remotely, which is, let's say, with cloud computing very much on vogue today, not so unusual. But here it's much more technical access in many ways, because the HPC machines are more or less for really experts in the field, scientific and engineering experts with applications that really require lots of computing, basically. And although there are lots of changes, we talked about that several years ago, we had this laptop here, which was cutting edge technology. Then suddenly, let's say 20 years later, we are in the domain of having, multi-cores. Now we are more or less in the many cores, where we have also accelerators, GPUs, and we're moving to this, as you have heard, 10 to the 18 exaflop performance rates now. And despite so many technology changes, and I was alluding to in the prologue that even this system, the Blue Gene series, was discontinued. So whole technology brands from IBM have just disappeared. But still, some of the technologies like UNIX is still on all the systems. The way how to access those systems with SSH is still done as basically 30 years ago. So in other words, these are really skills that you can reuse. And that's why it's also important to understand how we use a couple of UNIX commands here. So again, the system or one of the systems in the course will be the STEEP system. And it's basically developed by many different partners worldwide. You see different projects, the DEEP project in the beginning, the DEEPer project, the DeepPest project, and now we have even a new one called DeepC, which is a software for exascale architectures. And there are different partners, industry partners, academic partners, which basically develop this modular supercomputing architecture, which is more or less a new approach, really bringing different, let's say, modules together to achieve a goal that we also have heard a little bit in the prologue, and I will also pick on this in the introduction again. So basically, you see this modular supercomputing architecture with a cluster module, with high single thread performance, with all the different cores. But then you would have an extreme scale booster as well, which is much more for scaling out, for using maybe many different accelerators. And then you would have a data analytics module, which in the end is also something which has high memory for, let's say, software stacks like Apache Spark and so on. And here's an example of the nodes that you're probably also going to use here in the course. But let me go also to the website here, just to show you a little bit the scale of all of this. You see here from the Jülich Supercomputing Center, the website, and in Germany, one of the large research centers, and the Jülich Supercomputing Center is basically focused on delivering HPC services to end users, not only in Germany and the Helmholtz Association, also to Europe and actually worldwide. And you see here the production supercomputers with Juvels, Jureka, which are really on the forefront of computing, high up in the top 500. We will discuss this in the introductory lecture. But here you see more information if you want to look, what are these different modules? You see the cluster module, as I said, with many different nodes, basically, and racks with having, normal CPUs, but in a very good way. And it contrasts to perhaps the extreme scale booster that is much more on essentially using accelerators, right? And this is something where basically people have started to use those modules, of course, also combined with each other for doing several different elements in the applications. And then we have here the data analytics module, and we will use, of course, these through so-called login nodes and so on. And this is something that you also will learn through the course. Just that you see it has some practical impact. It is a prototype system, a test system, really at a large supercomputing center that you also use in the course. And let's go back a little bit to the slides. So in generally, when I do this practical lectures in the course, you will always see I have supporting slides when I show something. So basically, I try to cover most of the things I will show you in websites or via SSH and so forth. And it will be automatically also somehow in these slides. Another system that we're going to use is a very small system here at the University of Iceland. used for teaching. So it's not the production system of Iceland in terms of HPC. There we are currently deploying the ELIA system and had others basically in the past. But basically, this is a teaching cluster that we're also going to use in the course a little bit, but also the deep system we're going to use. Here, in order to get an account, it would be important that you go to UGLA under these interesting, let's say, URI that you always find in the bibliography here. And when you go to this web page, you will see there's a HPC application, and basically just fill that out and write Morris course here as the requirement, and then basically you get an account on this Jötunn teaching machine. The access to this is not necessarily so trivial. We will discuss this in the second part of the course today, how you can access it, but it is important for everyone here in the course. Your credentials for Canvas should also work in the UGLA, and in the UGLA you have this HPC service and to look at this. Of course, we can have also in Q&A session discuss this more if you have questions around this. Now let's come a little bit to this UNIX command, and I will jumpstart this a little bit by just logging into a system, but not explaining how we log in there. This will come in the second part of the lecture. But what is important to realize is with this command, and this is an SSH client that we will discuss later, I'm now in this deep test cluster already. So I logged in remotely, and what you see here, and I increase a little bit the font size, is basically this so-called UNIX environment. So here you have a command line interface where you basically can, now do UNIX commands. And essentially, when doing so, we have a lot of different options. One of it, of course, is mostly important to realize that I'm remote. Saying I'm hostname -a enables you to understand that this is actually a system called SAM 1015, somewhere in a domain from Germany, and it's called Deep. And basically with this, you realize directly I'm basically remote. And of course, to this, and also think about SSH, you would have a so-called username. One of the things to understand more and more in the next couple of lectures will be for you that these systems are shared with many different users. So everybody has a username on these systems. So you want to understand who you are, what you can do with who am I? And you see I'm Riedel1. These are accounts that are given to you. I also will explain how you get your account on deep systems for the course. But this is let's say also an important UNIX command here. And now you're wondering what happens if you do, this more and more, and your screen will be always full of text. There's, for instance, a clear command that you can basically have the whole screen clear. So basically you see there's less usage of the mouse. This is something which is, let's say, often new for people in the course, especially those that are operating in a Windows environment. So here we don't click on specific applications. Rather, we do something like this. Here is a list of all the different files in a specific directory, right? And you would have a pwd saying in which directory I am, print the working directory, and your working directory is the current directory on deep. So by doing so, and this ls-al really shows you a list of files, it shows you a list of directories. The difference you see here in the first place, so these are files, and here you have directories starting with the D, for instance. And you can imagine there are different files over the journey when you are basically part of this and of these HPC systems. Here you see, for instance, a long track record of HPC courses, HPC course fall 2019, our course from last year as an example, but then also, of course, student projects that have been used here on this particular deep system with me. Also specific machine learning and deep learning parts here that we have tackled. So essentially a collection of files, directories that some of you not really are so familiar with. So with cd change directory, you would go into this. And there's a couple of tricks I just want to convey briefly when you are in the environment of UNIX. I know for some it's really boring, but some people are very happy when I told them. There's a kind of completion by tab. So when you have HPC, you see here we could change into many of those. We have HPC, we have HPC course fall 2019, but also spring 2021. So, and to basically use now the tab, that gives you a chance, instead of typing everything manually, with a tab, you automatically complete what would be the best option. Now you see the next option would be fall or spring. Let's say we do fall. And then with a tab, one click, you can have the whole directory. You do enter and are much faster than typing it in completely by yourself. So I encourage you, when you get your account, experiment with the tab. It's very important to really use that. And here you see basically inside then this directory, you see many different files, obviously, that are there. And basically, can go to HPC, another directory. Oops, you see also important is the case sensitivity also here. What do I mean by this? I'll show you in a minute. That you have, for instance, here the HPC in capital, right? When you go here, let's clear it a bit so that we have it bigger. So in this particular directory, we have a directory called HPC, but when we do this, it will not work, right? It's not basically capital. And this shows you the case sensitivity here of UNIX, that you really have to use the bold letters in order to do this. And this goes for files, it goes for everything, essentially. Then there are many different commands I can show here. So in this sense, just take these as a kind of couple of those which are very important in the course. We also would say you will create some files. That's very obvious in the assignments. You will have some batch scripts and also some C programs to execute. And it's clear that this is not clear to you. We will see how that materializes then in the next lectures. But what I would suggest to you is, of course, creating a directory like we have seen before, right? So however you would like to call that, in the end, it's a bit up to you. But at least I would recommend you to create a directory where you put all your files in. And it could be named like this. And you do this with the mkdir, basically command. Again, you can use code completion. Let's say we have spring, but this time we want to have basically spring 2022. So by having this, you can change into this HPC course, in spring, and then basically create all your different files inside this. It sometimes helps you because if you use the system more and more, it becomes, flooded with different files if you've just, basically no directory for it. And now switch a little bit back to the slides so that you see essentially, as I promised in the ideas, basically here on slides and on the practical lectures, really know how it works. We could do the same in Jötunn. You see here the hostname -a. I show you later when we are connected. I skipped the fact how you basically access it with SSH. We will come to that later, basically. But here on the command line, you have all these commands for your references. We talked about who am I. Think about the PW, print working directory, which might be also important. We have the ls-al, which is then listing all the files and directories that I just have demonstrated. Of course, you can go on and go on, and basically there will be lots of other commands which might be very useful. And all the submit commands for jobs to a supercomputer, we will review again, of course, in one of the next practical lectures. So with this, we basically have done lots of essential elements here as well. There's one that is very specific to HPC, which is this module environment. That is something which is very powerful and needs to be included here as well, which is, of course, here on the Unix level, but it is something which is a kind of tool set in terms of installed tools, installed applications for HPC system, and then properly configured in a so-called module environment. So with this, you can load and unload modules. You can actually install the same software in different versions, which also makes sense sometimes. And it's really a neat tool, and you will see it today in almost all HPC systems worldwide. We will use it in the course maybe for an MPI compiler to really have, modules like GNU and others that we will load. So, and in order to understand what essentially modules are available, I would like to switch briefly again to the the practice here. We clear again the screen. It doesn't matter if you're in the directory or not, but you can do something like module avail. And here you have a list of all the different applications which are available at this deep cluster. CUDA are basically libraries for, NVIDIA, for the accelerators. We have application suites. We have Java indeed. There's HDF5, which is a file, basically a file format, a parallel file format we will talk about in one of our next lectures. We have Nickel as specific libraries again. So PyTorch is a deep learning library. Many of you know, of course, Python, but also R as a statistical learning package is there. Ruby, you see many different, let's say, applications and let's say drivers and libraries that you need for certain applications. Like cuDNN, for instance, is also very much known to be used in deep learning. When you basically have deep neural networks using accelerators, you need these libraries. But, we don't go into the details right now, just to show you that this module environment is a very, let's say, important tool, and you can access it here via the UNIX environment. And how you would actually load it is essentially this command module load. And then another trick perhaps is when you double click with the mouse on text here, you can copy and paste. I will demonstrate this maybe by loading briefly Python. Was an example here that the most of you are familiar. Double click and then the right mouse click, and you get copy pasted for what you basically have highlighted here. So another trick if you want for those who are not using Unix a lot. Another one that might be interesting for you as a tip is the arrow up. So essentially, if you do arrow up, you repeat the command that is before there, but also you can move through the history of commands you have executed previously. So of course, they would not make sense all the time, but you see every time when you do the move up button, you see my old, commands I have done way long before I even switched to the slide. So it keeps it available for you. And the same is, of course, then possible by moving down again to the latest, greatest command that we have just done. And of course, I should say it's, of course, possible to module unload, module load, and so forth. So another tip in the Unix area that I wanted to convey. So let's move back to the slides. So to see a little bit what's left there. Also, the dependencies here and there are important. When you do some modules and you want to load them, you will see that some of those will basically also require you other modules really to load before. So this is a kind of dependency setup as well, which is very important to realize. Interestingly enough, also you see in the list here, just because I forgot it, you have this different versions for the same software, which is here and there very much useful. An example was basically TensorFlow in the past, which has different versions, TensorFlow 1 dot something and TensorFlow 2 dot something, but still people have used that basically interchangeably. And so with this, you could actually operate them on the same supercomputer. Both of them, you just have to load the right module. Of course, you have to be careful thinking about Python. Even if Python is automatically loaded, it might not be the right version you need. So we basically also have to think about this, particularly on HPC machines, where you have, basically AI running, which is fueled by Python. We see this a little bit less in the HPC domain in terms of scientific applications, which are often, written in C programs. And in fact, many people have even Fortran. So this is an interesting fact that very old language, so to speak, is still used in the community of HPC every now and then. Examples include, for instance, computational fluid dynamics, which would have solvers in Fortran, but many other scientific domains as well. Good, but in a way, that's really all I wanted to say about module. There's module spider that you can also use as a command. But I think important is that once you get your accounts ready, just try it out, use it yourself, basically get to use a little bit the module environment, create directories, working with files, and maybe just one small hint before we have basically covered the main ingredients of the course here in terms of UNIX. In the first place is handling with files and creating files. Now this is an interesting editor called VI. It's basically the one editor that you basically find everywhere. It's a very basic editor, and hence the usability can be a bit tricky for students, as I learned in the past. So here you would basically perhaps go to our directory that we created. So you have here the HPC course Spring. So let's move into this. And what you do is VI test file maybe, and you create a file by basically now writing into this. And you would have a command structure. So E for insert, for instance, where you basically then have always a column to do something. And it's really easy if you try it yourself to understand what I mean. So welcome to our HPC course Spring 2022. And then you would press Escape to go back to the so-called command mode. So now I cannot type text anymore and would just do commands which actually then remove text. I would go to A, for instance, to append and edit again, edit a 2, escape again to basically go back to the command mode. And then when I do colon, I come to the specific command in question, like for instance, write and quit without questioning. And then basically this file gets got written. No rocket science, as you can imagine. It's obviously very similar, like you would create a new file in Windows with your mouse, but here we do it in the command line. We can rename this test file, let's say move to Morris file. It really doesn't matter. Basically with move, you cannot move only between the different, let's say, directories. You can rename the file. And when I do now, of course, do and VI this, we have still the same content. It's just a renaming of the file. So with this, it's of course important that you have, when you have your own files, your C programs, that you really understand the naming of that, because it can be very tricky in the HPC environment if your files are not correctly named and basically not at that location existing. It will be simply not executed, for instance, if it is a C program that basically was renamed and suddenly is not existing anymore in this particular directory. And the same goes, of course, if you do things like this, like as we discussed before. We basically have here, we of course want to have the Morris small file to the big capital. Remember that I told you that everything is case sensitive. Now, when you do the old one, like the small Morris file here, you will see there's nothing inside because it's a new file, right? It's not existing anymore because we just renamed it to capital Morris file. And also here you see when I just quit and not write, there will be even no file existing. So, and of course, it goes without questioning, if we go to the original Morris file, we have the content. But I mean, basically, this is all basic knowledge of UNIX. I know it's not apparent to everyone, especially those that are more into smartphones, more into Windows environments. But basically, from maybe thousands of commands that you can execute in the UNIX environment, if you master those that we have just discussed here today, and perhaps a couple of more that come, when we discuss about submission of jobs, compiling jobs. So if you have a couple of, commands at your disposal, you still can do a lot in this environment. So nobody of you needs to be a perfect UNIX expert in the course, but you need to have some UNIX skills to operate these HPC systems and to work with it. And with this, I'm really at the end of basically the first part of the lecture. Apparently, still the question remains how the heck I actually was coming here, because you remember, we are not anymore local on my laptop I use here for teaching. I'm on the supercomputer in Germany. And still the question goes how I went there, how I come there, and how I get the access. And this will be part of the second part of the lecture today. So let's move back to our slide set. We covered everything with this. And as I said earlier, the second part of this today from the lecture will be really then using SSH, understanding SSH in two different ways, using password and username, but also using SSH keys. So see you in the next part.